Hello everyone, I'm Ashwin Kulkarni. Welcome you all in this quantum computing learning journey. I hope you all are doing great, you are safe, and you are learning something new every day. Now, those who are following me from last a couple of videos, I have been focusing on mostly half-adder quantum circuit. So, my last to last video, I have explained theoretical part about half-adder circuit in quantum computing. In my last video, we have actually developed a circuit on IBM Quantum Lab where we have drag and drop the required gates to it. We have visualized it in the form of state vector or Q sphere, etc. Now there is a last part to it. Today we are going to write a code about it. How we are going to code half adder. The same circuit, everything will be same, but we are writing an actual code to build a half adder circuit, and we are going to simulate about it. So I hope you are going to like it. Let's get started. So let's get started. As you can see, I have opened a Jupyter notebook on my local machine. So how to install a Jupyter notebook and how to configure it to run a Python. I'll include that in the description section about the configuration of Python and the Jupyter environment into a system. So I'm not going into that. Okay. So now let's assume that I have already pre-installed everything, and I'm going to write my first program to run to simulate a quantum computer. Right now, here you can see there is one keyword called as Qiskit. Now Qiskit. This is pronounced as Qiskit. So, what is Qiskit? So, Qiskit is an open source SDK backed by IBM Research and a Qiskit community. It's an open source community. Anyone can go there and contribute to that. It has different libraries. One is Qiskit Terra, then Qiskit Air, and etc. So all of these libraries are useful for their own purpose. Now, what this Qiskit does is, so this Qiskit is useful to develop and manipulate the quantum programs in a Python, and you can run it on a quantum computer provided by IBM, or you can simulate it on your local machine. That's what it does. It's a SDK, and you can use it to essentially simulate or run quantum programs. Right now, it has a very good capabilities to create a circuit, and it has all the functions backed up there. You can visualize your circuit, you can play around it, and etc. etc. Okay, so first line, since how to install a Qiskit, I'll quickly go there. Now I'll attach this link as well in the description. Now here you can see the best way to install a Qiskit is via pip. Okay, so I know on the Mac users know about pip, and on other environments also how to install it. It all is already given here, right? So the supported platforms are Linux machines, Mac machines, and Windows as well. So everything you can follow here, and you can just get started with the Qiskit. All the requirement compatible Python versions, etc., etc. How to install it, you can get there. So I'll link this in the description. Okay. Now coming back to our program. So once you have installed Qiskit, you will see this particular. You can directly run it, and you can use it, and you can import it in your programs. Now, first thing in the first line, what I have written is from Qiskit import star. So, since this is not an in-depth video about Qiskit, I am not going into the specific functions of Qiskit. We are directly going to use the required functions from it. So I'm directly importing everything about it, so that so that you won't get confused, and you will not see much newer names here directly. Okay. Now, the next line is Qiskit visualization, where we can plot the block vector, and Again, we can plot the histogram. And the other one is Qiskit textbook, which will convert array to latex. I don't think we are going to use it. I have just imported it. Okay. Now, in the Jupyter notebook, I'm going to run this particular cell. So it is importing all the required libraries. Now, first things first, if you remember in our half adder circuit, what we require is we used two CX gate, which is C naught gates, if you remember, or please go check it out my previous two videos where I have explained the half adder in depth. Okay, now where we have used two C naught gates and one Toffoli gate. That's it. Then two qubit which are for inputs and two qubit which are used to store the outputs. One is for sum and one is for carry. That's how half adder is. It has just two input and the output are in the form of sum and carry. Okay. Now the similar way we need total four qubits, right? So we are going to define it as q equal to now. So you can just simply assume it here. Quantum register is just defining one qubit. Okay. Now I am defining four quantum registers. Now two classical registers to save the output. If you remember uh, then you or I'll put it here somewhere. So if you see this, we need two different gates, two different classical gates to store sum and carry as an output, right? Now we have classical registers. So now this all comes in your uh, Qiskit package, and then we are going to define your quantum circuit. So which has your Q and C. That's it, right? Now if I run this, I hope this should run. Okay. Now let's define a half adder function. So in Python, we can define a function like this. We should provide a def keyword and then the function name and input parameters. So two different qubits which are going to act as input, and then one qubit is for sum, one is for carry. This is how we require our uh, or inputs for half adder inputs, and basically the qubit required to store inputs and outputs. Now first of all, what we have done is, so we need to define C naught gate. So if you remember, so to define a C naught gate, what you need to do is you just need to use your quantum circuit dot. It will provide all of your available gates there. So we are going to use C naught gate here. So it will simply qc.cx. Now what we are going to do is I'll explain. Okay, Q of S, right? So the C naught gate is basically a two qubit gate where one qubit act as control bit and other is target bit. So again, I'd urge you to just go check it out my previous two videos for half address. This will be very much easier for you to understand this video after that. Now the C naught gate we are defining from one input gate to the other sum gate. Now, similarly, the other we need to define C naught gate from other qubit, right? So these two are going to be used for sum, and now there will be one Toffoli gate which will be called as CCX, which is three qubit gate to right. Okay, so Toffoli gate will get activated if both of these input qubits are 1, and that's when your carry will be 1 if both your addition qubits are 1. Okay, now this is your half adder circuit. If I run this cell, yeah, this is yeah, this is quickly ran. Now the next task is, now we need to call basically this particular half adder and we need to use it. Okay. Now, what you need to do is, first of all, we need to call this circuit, right? Now, our first two qubits, which are 0 and 1, will act as input qubits. Now, this 0, 1. Now, the third qubit, which is indexed by 2, will act as sum, and the last qubit will act as carry. So that's how we are passing 0, 1, 2, 3 respectively for A, B, S, C, right, in the half adder circuit. Okay. Now, now here nothing happens because this has just configured your quantum circuit. You cannot see it, or you cannot we haven't ran it basically. Now, you remember we need to measure the output of sum and carry in some classical bits, right? So that's where you need to have QC dot measure, where you can just get your output to classical bit. And similarly again, QC dot measure Q3 to C1, right? So yeah, so this is how what we have done here is our sum and carry will be on qubit 2 and 3 with 0 indexing. We are just getting those outputs from qubit 2 to classical register 0 and qubit 3 to classical register 1. That's it. Nothing rocket science here. Now our setup is done and everything is done. If I can draw here the circuit, let's see, I'm able to draw. Yeah, okay. I need to run it beginning. Okay, so now you can easily correlate it with all our two previous videos. So here, what simply we have is we have one C naught gate from 0 to 2, one again C naught gate from 1 to 2, one Toffoli gate from 0, 1 to 3, and our measurement. That's it. Okay. Now I'm just commenting out here, or we'll again represent it later. Now we need to run this on a simulator. So in the last video where we have used Quantum Lab, so in the back end, what it has done is it was running whatever our circuit that we have created. It was running on the air simulator. Okay, so what is air? So first of all, let me write it. So to define backend, we need to have air library dot get backend. I hope this is correct. And Quantum simulator. I hope this is correct. Okay. Yeah. So, what is this Quantum simulator? What is this air backend? Okay. So basically, air is a simulator which is written in C++ for high performance. Core written in C++ is used to simulate your circuit written using Terra libraries. Now, what it does is it just gets your quantum circuit and simulate it, or we can use the actual quantum computer provided by IBM. You can get a token for that and you can queue your job there. So that also Air does. But here we are going to simulate it on our local machines. So that's why we are going to use this Air and get backend in the form of Quantum simulator. Now, what is Quantum simulator? Again, there are three different types of simulator, and there are many, but the important ones are Quantum simulator, state vector simulator, and unitary simulator. Um, Oh, this might be again very much overwhelming for you. We will get into it later, but just simply the Quantum simulator is run your quantum circuit, and it is pretty much noise reduction based simulator. Now, what you need to we need to execute it. So execute is again provided by Qiskit. So what we need to pass here is our quantum circuit, our backend, and shots is the third parameter, which is 1000. So what is shots? It will run your simulation 1000 times to check the output, and it gets averaged out, or yeah, average out your probabilities. Now we have everything ready. We just need to run our simulator, and we just need to get our output done. Okay. Now, to get result, what we need to do is job dot result. The spelling is correct, right? Okay. So what this line does is, whatever we have created a job to execute our quantum circuit, we just need to get result of that performed job. Now, to get count, so what this count will mean is, I'll explain once. So get count. Oh, sorry. Yeah, okay. Think it is get counts. And we'll print this count. And at last, again, if you want to draw a circuit. By the way, what is MPL here? Can you try to guess it? MPL, what we use to draw in Python, MPL. Okay, I'll tell you, it's a matplotlib. So basically, in Python, we use matplotlib library predominantly to draw our circuits or draw our whatever graphs or anything in Python. So that's how it uses in the backend this particular kc.draw function if we provide MPL to it. Now let's run it. It will take your time, and yes, it is. Again, I need to run it from beginning. Don't get confused. Yeah. So you can see here your count of 00 has come 1000 times. Why is it so? Because our particular this two qubits are 00 state. So of course your sum and your carry, which is in the two classical registers 0 and 1, will be 00 always in any case. Now let's change our inputs a little bit. So what we will do is we'll introduce to 0. Okay. So what we are doing is, our first bit we are making it to 1. In this case, your sum should be 1 and carry should be 0, right? So run this circuit again. Okay, got it. So essentially on the first output register, we are uh, returning carry, and the 0th one we are returning sum. So that's how we have run this circuit for 1000 times. Still, in all 1000 cases, you have got your output as 0, 1. What this means is your sum is 1 and your carry is 0. Okay. Now let's make it to qc.x of 1. What we are doing here is we are providing both of your qubits as 1. That means in this case, your sum should be 0 and carry should be 1. Let's see if our assumption is correct and what we have learned for half adder is correct or not. Okay, cool. So as you can see here, now your sum is 0 and your carry is 1. Since we are storing our carry in the first quantum registers and we are reading it from right to left, so your carry is 1, your sum is 0. And yeah, this is it. You have written your first code for your quantum computer. It's pretty much easy, and it's pretty much interesting as well, right? So I hope you have liked it, and I think it's for any particular doubts, you can just ping me or you can put it in the comments. I'll able to help you out for sure. Okay. So moving on to the next section. An interesting quantum news of this particular week is again related to IBM, since IBM is doing a lot in this area. So IBM has announced its mainframe system called a Z16. What is mainframe? So you would have seen in movies or in pictures or maybe in real time a big computers where those data centers are there, and just every wires are connected to it and all that stuff. So that is called a big data centers where your computation happens. So that is called as mainframes, and IBM has taken a leap into it and released its latest versions. So there are still 2 out of 3. So basically 66% of Fortune 500 companies are still running on those mainframes. Now, what IBM has done in terms of quantum for those mainframes is they have released it as industry first quantum safe mainframes. What does that mean is, now whatever computation that is going to happen on those systems will be secured for current classical security algorithms as well as future quantum related algorithms as well. So if you remember, in my first or second video I had talked about the quantum threat that is going to be there for the upcoming systems, and all the system needs to be changed accordingly. So already IBM has taken that leap, and all the mainframe systems, so most of the banks, financial things, or US government organizations, whoever are using that will be quantum safe in the industry first. Isn't that cool? So I hope you have liked this video and you have learned something new out of it. If yes, then please do comment below, and please like this video and share it with your friends as well. So anyone who is going to jump into this particular area should get help out of it. Yeah. Okay, so thank you so much for again listening to me, bearing with me till here. I hope to see you in the next video. Bye.